So last time we left off with David Hilbert, one of the most influential mathematicians ever. In the year 1900, he got up and he gave a list of 23 open problems to the mathematical community, and we worked on it ever since, and we're still working on it, almost a century and a half later. He could also contributed to relativity theory, influenced the work of many other luminaries that came after him, including Gödel and Church and Turing himself. John von Neumann was his lab assistant, actually, was his RA. That's pretty impressive. And here are some of the books by Hilbert and about Hilbert. He did work in almost every mathematical field there was. Many things are named after him. So, for example, we have Hilbert's axioms. He tried to re-axiomatize set theory to do away with Russell's paradox. He has metric spaces named after him, infinite dimensional Hilbert spaces. Hilbert curves, which are space-filling curves. Here's a 2D version, here's a 3D version. They occur in arbitrary dimensions. He popularized the infinite hotel paradox that Cantor came up with, and so he helped basically popularize and help make mainstream Cantor's work on transfinite arithmetic, on which a lot of the course material is based: diagonalization, dovetailing, one-to-one correspondences, and so on. And so his 23 problems set the direction for basically all of 20th century mathematics, and still does. So that's tremendous impact. Here's direct quotations from his famous address of 1900 to the Congress of Mathematics in Paris. And he basically said that in order to see the future, you have to have some sort of a roadmap, and we'd all like to see where we're going. And here's a list of problems that will help guide us. And some of those problems were open already before he put an even larger emphasis and bounty on them. So he said the mathematical theory is not considered complete until you have made clear, you've made it so clear that you can explain it to the person on the street, basically, which is kind of reference to Occam's razor: beautiful proofs, elegant proofs, proofs that engage our intuition rather than fly in the face of it. So we're going to go through all 23 problems, actually. Some will go very briefly for a few seconds, but others will harp on that are even specifically more relevant to computer science theory and undecidability and Turing's work and Gödel's work. So first, a continuum hypothesis, basically. So he gave Cantor problem number one. Basically, the problem states, is there an infinity between the countable infinity of the integers and the uncountable infinity of the reals? Is there something in between, some intermediate infinity? And Cantor already kind of stated that problem and couldn't resolve it. So not until 1963, so almost 2/3 of a century later, that problem was proven to be independent of the axioms. Independent of the axiom means you can take that statement of the continuum hypothesis and, in the affirmative, say that there is an infinity between the integers and the reals that's strictly greater than the integers, strictly less than the reals, and go with that, and the system, your axiomatic system, will not become inconsistent, assuming that it was not inconsistent before you started doing this. Or you can take the negation of the statement. You can say, there is no infinity between the integers and the reals. Go with that, make that a new axiom, and that will not change the consistency of your system again, which is an interesting status or disposition for an axiom to have. In other words, you can have it your way, one way or the other. And we already seen this phenomena in non-Euclidean geometry with a parallel postulate, right? Euclid's parallel postulate, line and a point off the line, whether there's exactly one line passing through that point parallel to the first line. In attempts to prove that from the other Euclid's axioms, we got non-Euclidean geometry, spherical geometry, hyperbolic geometry, and later we found through Einstein that the universe, the very universe we live in, is not Euclidean, actually. It's hyperbolic, actually. So that was resolved in an interesting way. At the time that Hilbert stated this problem, it didn't occur to anybody that this could be the case, that the continuum hypothesis could be independent of the axioms. Problem number 2, prove that the axioms of arithmetic are consistent. Right? So Gödel settled that in the 1930s in a very interesting way. He proved that every formal axiomatic system is incomplete. That is, any system consists of axioms and ways of bashing axioms together to create lemmas and then theorems and then corollaries, and so, i.e., any kind of mathematical system that we know of must have statements in there that are true but not provable, assuming it's consistent. So that means it's incomplete. There are things that are true that you can never prove. Not because you're not smart enough or we're not smart enough or some ancient, omniscient entity cannot prove it either, because the proofs themselves don't exist for certain true theorems. He showed that's true not just about our mathematics, but about any formal axiomatic system whatsoever. So that kind of, we'll talk more about that when we talk about Gödel. But that's how that problem was resolved, problem number 2 of Hilbert. Problem number 3, given any two polyhedra, basically, is it possible to dissect one into pieces and reassemble it into the other, assuming they have the same area, in 3D, the same volume, and so on, or in our higher dimension, the same hypervolume. So in 2D, it was settled very nicely. Basically, somebody showed that you can take any two equal area polygons, no matter what their shapes are, dissect one into pieces, into a finite number of pieces, and reassemble it exactly into the other, without any overlap, having the same area. So for example, here are some constructions, dissections. So each pair of these is a dissection of one into the other. So here's a dissection of a square into a triangle, like we just saw on the previous slide. This one's called a hinge dissection because these are, so you can consider those to be hinges here, here, and here, and you can actually unhinge, unfold, and reassemble it in a continuous hinged way, which is even more constrained than just arbitrary reassembly with shuffling the pieces. So here's interesting, a 10-gon can be reassembled into a 9-gon in this fashion, and so on and so on. Here's a 9-gon into a 4-gon, which is a square, right? Here's a 7-gon into a triangle reassembled. And you can go on and on about these dissections. And so the general theorem is that any figure can be reassembled into any other figure whatsoever, assuming that their areas are the same to begin with. That was a surprise, that they were such a general, ubiquitous phenomena. So that's Hilbert's problem number 3. And we'll talk a little bit more about that in higher dimensions. But some of these other problems we'll just kind of skip over: continuous groups, metrics, and geodesics, and so on. But these dissections get, quite interesting. We'll talk more about space-filling tessellations in a few minutes. Problem number 6, he said, axiomatize all physics. What could be simpler than that, right? Very short description. Of course, very, very deep problem. Einstein took a look at this problem in 1900, thought about it a lot, and invented relativity as an attempt to solve this. A few other people looked at it from a different perspective, from a perspective of the very small rather than the very big, like universe scale problems. They looked at atomic scale problems or particle scale problems, and they came up with quantum mechanics. Again, this arose directly out of Hilbert's challenge to axiomatize physics and put it on a mathematical, rigorous footing. And Hilbert himself made all sorts of significant contributions to relativity theory and other aspects of physics. In fact, he discovered Einstein's general relativity field equations before Einstein did. Einstein was working on it from 1905 when he published special relativity to 1915 when he published, 10 years later, general relativity. And somewhere in between, Hilbert figured it out first. But out of deference to Einstein, because it was Einstein's baby, his whole theory, he kind of stepped back and didn't publish it and let Einstein publish it instead. And, so that's impressive. Problem number 7 is A to the B transcendental in general for algebraic numbers A and B, or irrational numbers A and B. That's actually a very deep set of problems. So for example, we can prove that e to the pi is transcendental. Transcendental, by the way, means it's not the root of some polynomial. So it's not an algebraic number like square root of 2 or square root of 5 or other numbers involving roots and addition and multiplication and subtraction. In other words, roots of polynomials with integer coefficients or more generally rational coefficients, that they're transcendental numbers like e and pi that are not roots of polynomials. That's what transcendental means. So in general, it's hard to tell if a number has this property. And some of them are very much open after centuries of us trying to prove whether they're irrational but algebraic or irrational and transcendental. So for example, we don't even know if e to the pi is transcendental. In fact, we don't even know if it's irrational, e to the pi. We know that pi, we don't know the irrationality or irrationality of pi to the e, strangely enough. We know that e to the pi is irrational, but we don't know about pi to the e the other way around. It's open. If you can resolve, or 2 to the e, or even pi plus e. We don't even know if pi plus e is rational. It's an open question. We don't think it's rational, but nobody can prove it. You know? Or pi divided by e and so on. So that's this whole family of kind of questions is Hilbert's problem number 6. Problem number 8 is a biggie, the Riemann hypothesis. So basically it talks about the Riemann zeta function, and that's all it is, all in quotes, because it's a very profound and complicated function, not in the way it's presented. It has a very simple form. It's just powers. It's just infinite sum of powers. But it relates to the distribution of primes and to many other aspects of mathematics. There's even algorithms in computer science whose runtime depends on the Riemann zeta function and the Riemann hypothesis. There's algorithms whose runtime is quantified as follows. This algorithm runs in polynomial time if and only if the Riemann hypothesis is true. Strange. How many have heard of that? It's a very strange way to characterize the runtime of an algorithm based on an open mathematical question that's been open for centuries about this weird continuous analytic function. There's applications in cryptography and security and so on. It's just this function appears all over the place. And the Riemann hypothesis basically says that the real part of all the non-trivial zeros of this function, the real part of all of them is 1/2. The imaginary part can vary. And it's the second part of this problem number 8 of Hilbert's is the Goldbach conjecture. The Goldbach conjecture says that every even number bigger than 2 can be written as a sum of 2 prime numbers. So like 12, for example, is equal to 5 plus 7. It's also, and it can be represented by other pairs as well, not necessarily uniquely as a sum of 2 primes, but at least once. That's also open for a couple hundred years now. Nobody knows. So the Riemann hypothesis has been open since 1850s roughly. The Goldbach conjecture has been open even longer than that, almost 3 centuries. We know that the Goldbach conjecture is true for the first 10 trillion first 10 trillion values. So you can numerically, confirm some of these to a lot of values. The first, billions or trillions or quadrillions of values, but that doesn't prove anything, right? There's all sorts of interesting mathematical statements that, like formulas, that the formula, so-called identities, where it's true for the first, 10 to the 20 values, but it's false for the next one. So the first, counterexample is 20 digits long. For some mathematical statements or formulas that would be identities, but not quite identities because they're false, but it's very hard to find counterexamples, and the smallest counterexamples are huge. So this is evidence that it's true, but it's not a proof, obviously. You can't empirically, by lots of examples, prove something, obviously. Law of the reciprocity, didn't get a lot of airtime, but so here's the Goldbach conjecture for the first 1,000 even numbers. This is the number of ways each one of these numbers can be written as the sum of 2 primes. So it's not even close to unique. So for example, numbers around 1,000 could be written as the sum of 2 primes in at least 20 or 30 or 40 or 50 ways for some of them. And here's the graph for up to 1 million. So numbers in the range of 1 million or so can be written as a sum of primes in at least 3,000 ways, and some of them can be written in 10,000 ways, different ways, as a sum of 2 primes. So it's not even unique. Again, this is not proof, it's evidence. that Goldbach conjecture is probably true. And partial results have included things of the form, every sufficiently large even number could be written either as a sum of two primes or the sum of a prime and the product of two primes. So it's not quite Goldbach's conjecture, it's close. And we've known things like that for a while. More lately, we know that Goldbach conjecture is true if you allow the sum of at most 6 primes. That we can prove, that no more than 6 primes are needed to add up together to any even number bigger than 2. And there's entire books written about this. In fact, there's entire books written about each and every one of those problems, each and every one of the 23 problems that, many, many books, not just one. So here are some of the books on the Riemann hypothesis, for example. Sometimes it's called, the greatest unsolved problem in mathematics. The zeta function appears in lots and lots of places. Just some of the books written on that single individual function that Hilbert helped make famous by naming it. In fact, the Clay Mathematics Institute has $1 million prize for the solution of the Riemann hypothesis. To this day, nobody's claimed it. Some of the other problems, the Poincaré conjecture actually has been solved. So they list 7 different problems. One of them is P is equal to NP, right there. You might have heard of that one. Still unsolved after 45 years or so. It's been open. And the Riemann hypothesis is number 6. But let me just say, this isn't the easiest way to make $1 million. People have been working on these problems for a long, long time. In some of these cases, centuries. So problem number 10, that's a particularly interesting one. We'll talk quite a bit about that. So Hilbert said, basically, find an algorithm to determine whether a given polynomial equation has integer solutions. Right? So for example, here's a polynomial equation. It happens to be the Pythagorean theorem, right? X squared plus y squared is z squared. Has many integer solutions. Here's one solution. 3 squared plus 4 squared is 5 squared, right? 9 plus 16 is 25. It has many other integer solutions. And in general, you have a polynomial and a bunch of variables. See if it has a solution or not. What can be easier than that, right? So for example, x to the 9 plus 9 to the 9 plus y to the 9 is equal to z to the 9 has no solutions. We know that because it's a corollary of Fermat's last theorem, and which basically says that all generalizations of Pythagorean theorem to higher exponents than 2 have no solutions in integers whatsoever. So Andrew Wiles proved that in 1995 after 3.5 centuries of it being open due to Pierre Fermat. So notice that he didn't say, is there an algorithm? He said, find an algorithm, meaning that he thought that there is one, and it didn't occur to anybody at the time, including to Hilbert, and he was a very, very smart guy, that there are some problems for which there are no algorithms. That was news to us, care of Turing, 1936. Turing was the first to show that some problems, simple though they are to state, have no algorithms whatsoever, not even in theory, which is kind of amazing. We already proved that in class a few weeks ago, that the halting problem, for example, is one of those. Very easy to state, very simple binary predicate, yes, no, whether a program halts or doesn't halt. That has no solution in algorithms. So Hilbert didn't even think about that possibility, actually, which is interesting. But he was asking this about Diophantine equations, which are just basically polynomials over integers. So let me show you why it's so difficult. If I ask you, is there an integer solution for x cubed plus y cubed plus z cubed is equal to 29? What would you say to that? Is there an integer triplet x, y, and z such that their cubes add up to 29? What do you say? Sure, like what? 3, 1, 1, obviously. Easy, right? So why is this problem hard? Well, if I ask you this question about 30, sum of 3 cubes equal to 30, this will take you longer, and there is a solution. It's just looks like this. For this triple of integers, a couple of them are negative, notice. The sum of their cubes is 30, it turns out. I didn't believe this either until I plugged it into Wolfram Alpha on the web, and sure enough, it is equal to 30. I mean, it's unbelievable, right, when you first see it. You can also do this using Google Calculator. Wolfram Alpha is pretty good. Okay, so what if I said 33? X cubed plus Y cubed plus Z cubed, is there a solution for a triple of integers X, Y, and Z such that the sum of their cubes is equal to 33? That's unknown to all of humanity. Nobody knows. And if you can resolve this one, you can probably get an immediate PhD in mathematics, plus all sorts of interesting job offers from NSA or stuff. It's pretty amazing that the complexity of this problem, look how it explodes. It goes, you set the parameter to 29, it's trivial. You all got that one. You set it to one more, 30, and it becomes horribly complicated solution. You set it to 3 more, 33, and nobody knows. Nobody can tell to this day. And a lot of people have been working on this particular equation. And that's just one equation. Hilbert was asking about the general case, arbitrary polynomial equations. But other things we do know. So, for example, we don't know if any integer can be represented as a sum of 3 cubes, because we don't know if it's true of all the integers, and we don't even know if there's an algorithm to determine that. For sure, yes or no. In either case, an always halt. If it is true, you will find it out eventually. What's an algorithm that will eventually detect a triple if a triple does exist? How would you implement that? And I don't care about efficiency. Don't worry about efficiency. How would you implement that right now in a few lines of code to look for 3 integers whose sum of cubes is equal to 33, assuming it exists, such a triple exists? How would you do it? It's not hard. Brute force. And what does brute force mean exactly here? More specifically, enumerate all values, and make sure you go positive and negative, so you don't just go positive and you got to go some negative on some of them, and that's okay. And eventually, if it exists, you'll find it. But if it doesn't exist, you won't find it, and your algorithm will be inconclusive whether it exists or doesn't exist, because you'll be running forever, and you'll never know how high you need to go, and there's no upper bound, right? I mean, these numbers are in the millions and trillions, and the sum of cubes adds up to 30, 33, or to 30 in this case, I guess. So very, very tricky business. But there are things we do know. So for example, we know that every integer can be represented as a sum of 4 squares. That much we know. And that's always true. And in fact, many integers don't even require 4 squares. 3 squares or even 2 squares are enough. Because one of the squares is 1, right? 1 squared is 1. So another square is 4. So you have a lot of leeway. So that much we know. That's a theorem by Lagrange, actually. So fast forward to 1970, which is 2/3 of a century after Hilbert posed that problem about Diophantine equations, polynomial roots, and he proved that every Turing enumerable set is Diophantine. We already talked about what it means for a set to be enumerable, basically recognizable is what this means. It's Turing recognizable. There's an algorithm that flags down all the yes instances. Basically, it's all the language. It's every language that's the set of strings recognized by some Turing machine, right? So a set is enumerable or recognizable if and only if there's a Turing machine that accepts that set and precisely that set, accepts everything in a set and rejects everything not in a set of numbers or strings. Numbers and strings are interchangeable, right, by dovetailing. So he showed that he showed a very strong result. He showed that every Turing recognizable set is the positive values of some polynomial equation, of some polynomial, let's put it that way, the positive value of some polynomial with enough variables. So for example, the set of prime numbers is exactly the positive values of this following polynomial. And to be sure, it's a long polynomial and it has about 26 variables, and that's fine, and it has a very high degree. The degree is, this term here is 2 and 4 and 2, that's 6. And squared as a degree of that term by itself is the degree 12, right? And there might be other higher degrees in here. But the set of prime numbers is exactly the positive values of this polynomial, no more, no less, as all the variables range freely over the entire set of integers for each variable. Now, I actually implemented this. I plugged in arbitrary random values for the a through z variables here, and I was hoping to get large primes out of it. But all I got was negative numbers. Remember, the set of prime numbers is exactly the positive values of this expression. So it's actually hard to get positive values of it, but it's a true statement nevertheless. Now, how did he figure this out? Obviously not by trial and error. It's just too horrendous to contemplate, even by a machine. It's such a complicated polynomial. But he showed something much more profound. He showed that every Turing machine can be converted to a polynomial that does the same thing as the machine. If the machine accepts a number, that polynomial will have that number as one of its positive values. And conversely, if that Turing machine rejects or doesn't accept a particular number, or equivalently a string by dovetailing, this polynomial will have that as one of its negative values. And he showed a general reduction of how to do this. And he showed something even more mind-boggling. Because there's a universal Turing machine that does the job of every other machine, like a compiler does, there's also a corresponding polynomial that behaves at your option like any other polynomial that you wish. So the first parameter is the actual index of some other polynomial, and then varying this number will make this polynomial p with all these other variables, all these other k variables, and k could be large, but that's okay, it's a fixed finite k. Based on what the green parameter is, n0, this red p will behave as any other polynomial. In other words, it'll coincide with arbitrary other polynomials indexed by this parameter. And just like a compiler will behave just like any other program you'd like if you feed it the right input, the right string. So if you want your compiler, so a compiler is like a super program that can do the job of any other program based on what you give it as input. And if you give it the right input, this compiler could play tic-tac-toe with you, or take you shopping on the web, or run an operating system for you. And what is this input to the compiler code? You've all done this. What is it called? This input to the compiler that will make the compiler do arbitrarily clever things. Your program. Your program is the input to the compiler. So this is the program right here. The program to this polynomial. Or the program to the universal Turing machine that will make it, it's a set of instructions basically, but it's encoded as a number, as an integer. That's okay. It's interpreted as a set of instructions. A program and an integer are interchangeable. How many get that? It's called dovetailing, right? Take the program, represented as a one long string. It's now a bunch of bits, end to end between the quotes. That's your program. A bunch of bits. A bunch of bits could be represented as a number. In fact, it is a number. It's a very big binary number. So if I say program number 43, we all know what it is. If you start decoding that 43 into C syntax or Java syntax or whatever. So he showed that polynomials can compute arbitrary functions, arbitrary computations, arbitrary algorithms. They can simulate arbitrary Turing machines. That's an amazing result, because you look at the polynomial and it doesn't look like much, right? I mean, this one looks formidable, right? But this polynomial looks pretty straightforward. Sum of 3 cubes. But now you know why polynomials are so difficult to analyze and predict and track their values and see what they do and don't do and what values they take on and don't take on, because they're equivalent to arbitrary programs. And that's why it's so hard to analyze them. And that's why when Hilbert said, find an algorithm that determines what an arbitrary polynomial does or doesn't do in terms of its values, whether it has roots in integers or not, or whatever, it's an undecidable question. So he asks for an algorithm for an undecidable question without knowing that he's doing that. Smart though he was, the whole concept of undecidability didn't exist back in 1900. We first discovered that in 1936. And we thank Turing for that. And that's how this problem was resolved, Hilbert's 10th problem. There's all sorts of other issues about the problem. That's just the tip of a giant iceberg that's still ongoing to this day, actually. Right, so this is a universal polynomial corresponding to a universal Turing machine, and And then another set of questions about that is how small or big is the degree? So yeah, you can have a universal polynomial that acts as a universal Turing machine like a compiler does, but how small can you make its degree? Well, it turns out degree 4 suffices. So you don't even need arbitrary larger degrees than 4 to have universal computation kind of behavior in polynomials. The polynomials with degree 4 or less are as complicated as any other thing. You have a universal polynomial of degree 4 or less. Now, don't get me wrong, the degree 4 polynomial will be very complicated. And there's a trade-off, in the degree and the number of variables, right? So so you might ask separately, how many variables suffice? Maybe the degree could be 4, but you need, a trillion variables, a through z plus a trillion more. No, it turns out that 9 variables suffice. Polynomials of 9 variables or less can already do arbitrary computations that can simulate arbitrary Turing machines. But there's a huge dramatic trade-off between these two quantities, the number of variables and the degree of the polynomial. Right? So we already saw that the prime polynomial that we gave earlier has a pretty high degree of, I don't know, whatever it is, 20 or so, 15 or whatever it is. And this problem is equivalent to finding small universal Turing machines. In other words, compilers that are as small as possible. So here is some, kind of a taste of this trade-offs, just so you can see some more details on that. And all these things are ongoing lines of research, and it gets very esoteric. But there's a universal polynomial of 58 variables in degree 4. And if you want to reduce the number of variables to 28, the degree may have to go up to 20. And if you want 19 variables only, the degree will be 2,000 something. But if you want 13 variables only, you need 10 to the 43 degree, potentially. These are upper bounds. These are not exact numbers. And if you want 9 variables, the degree may have to be as high as 10 to the 45, which is like halfway, to a googol, closer to the square root of a googol, right? And there's a whole bunch of lines of research around that, and So, so Hilbert's problem was about integer solutions to Diophantine equations, to polynomial equations in many variables. If you change that to rational solutions, a little more general than integers, because integers are rational numbers, but rational numbers are not necessarily integers like 2/3 or 1 1/4. It's still open, whether there is or there isn't an algorithm. We don't know that it's undecidable, and we don't have an algorithm for it either. After all this time, it's still open. And just so you don't think this is an ancient problem from 1900 or even 1970, there's a conference just a decade ago, and there's still on ones that are even more recent, about Hilbert's 10th problem. So he gave a list of 23, and this is number 10, and there's still ongoing modern recurring conferences on individual problems of Hilbert, even after a century and a third or so of him stating these things. So it's quite amazing. This is just to show you kind of a tip of an iceberg, kind of how big the impact is, by showing you even a sliver. And of course, in this conference, Matiyasevich himself showed up and gave a couple of talks. And Julia Robinson did some of the groundbreaking work on which Matiyasevich based his solution for Hilbert's 10th problem. She was a mathematician in the 1930s and 40s and 50s, and one of the early women mathematicians. So she gets a lot of credit, not just being for a great mathematician, but breaking into a field that was male-dominated, mathematics, very early on, more than a century ago or so, roughly a century ago, almost a century ago. Okay, so by the way, if there's any questions or comments, feel free to ask me. So I'm getting, why am I showing? Yeah, go ahead. So that's a good question. When you have Boolean formulas, things simplify because you only have 2 values, not an infinity of values. But they still remain very complicated even then, because if you have arbitrary Boolean formulas and you try to see what they do and don't do, that's satisfiability. That's a problem of satisfiability, which is NP-complete. So it's still a very hard problem, but it's not undecidable because there's only a finite number of choices. Each variable can just be 0, 1. And even if you have 500 variables, that's only 2 to the 500 different choices for the x's, the y's, the z's, the w's, and all of 500 other variables. And you can brute force go through all of them and see what's going on with this polynomial, quote unquote, or more precisely, Boolean formula or propositional formula. So then it becomes decidable, but even within that, it's still very complicated. And it's the hardest problem in NP. It's the satisfiability to figure out what's going on with these polynomials in Boolean form. And he was saying that and corresponds to multiplication and or corresponds to union or addition, I guess. So good question. That's a connection, definitely a connection to this. Any other thoughts or questions? So some other problems we're just going to breeze over, things about quadratic forms and seventh degree equations, finiteness of certain systems, and there's a lot going on here, but since this is not a math course, we'll just harp on the interesting stuff more and kind of gloss over the other ones. But at least once in your life, you should see all 23 problems in one place at one time, and this is it. Today is the day for that, because it made such an impact on all of mathematics, science, and physics that gotta give it some respect, right? So rational functions, algebraic curves. This one is particularly interesting. I'm going to talk a lot about this one. So non-regular space-filling polyhedron. So it's about sphere packing and tiling. Specifically about anisohedral tilings. So you've all seen tilings, right? The ceiling is tiled with rectangles, right? Your bathroom is tiled with either hexagons or triangles or squares. Tilings are everywhere, right? But there's very interesting problems about tiling and also about sphere packing. So sphere packing, right, you go to the supermarket, you see oranges kind of stacked this way. And why are they stacked this way, not just thrown arbitrarily? Because this is a close packing. You can pack the most number of spheres in this configuration, and it gives you the densest number, way to pack identical spheres to minimize the space between them. Because, when you ship stuff, you want to kind of cram them into a smaller volume so the container will be smaller so that it'll fit more in a truck and so on. Now, for centuries, people believe that this is the smallest way to pack spheres, right? Just like you'd imagine, like in a pyramid kind of shape. But nobody can prove it. Only after 3 centuries, finally somebody proved it just a few years ago, actually, like a decade or early 2000s or something like that, or late 90s maybe, was relatively recently, because this was open for centuries. Ever since Kepler, so open for almost 4 centuries, whether this is the best way to pack spheres in 3D. Now, this problem exists in every other dimension too, right? What's the best way to pack things in 2 dimensions? In other words, if you arrange pennies around the central penny, how many pennies can touch the central penny simultaneously? Penny coins, right? How many? 6? Could you get 7? No, not in 2 dimensions, right? So you can have, 6 pennies all touching, the central penny there. It's called the kissing number because they all kind of kiss the central penny. And 6 is the limit for 2D. For 3D, how many tennis balls do you think can touch a central tennis ball, or oranges or whatever, marbles? What's the number for 3 dimensions? Take a wild guess. 16? 17? See, it's less obvious, right? It's got to be at least 6, right? Because 6 is already true for 3. You can do this with marbles or tennis balls, but you can put a few on top and a few on the bottom. How many on top and how many on the bottom? So I hear 16, I hear 21. 5 on top, 5 on the bottom, so that's 10 plus 6, that's 16. What do you guys say? 3 on top, 3 on the bottom, so that would be 12 total, 6 around, and then 3 and 3 is 6 plus 3 plus 3 is 12. So I hear 12. How many think 12 is the number? Turns out it's 12. Now, just because that maximum kissing number is 12 doesn't mean that if you keep replicating that in a regular pattern, that's the best density you can achieve in 3D arbitrarily far. How many understand that? That's not obvious at all, but that happens to be true. Let me show you an interesting packing problem. So if you have a 10 by 10 and square, and you want to fill it with 1 by 1, so how many 1 by 1s can fit at most into a 10 by 10? 100. There's no two ways about it. At most 100. But if I make this an 11 by 11, the number will be 121. All right? But what if I make it 10.1 by 10.1? So certainly 100 will still fit with a sliver margin on both ends here, bottom and top. But it turns out that you can start jiggle them in, and of course they can't overlap either. There's no tricks here. So you'd think that you couldn't utilize this space and this being 10 by 0.1 and this being 10 by 0.1, right? So there's roughly 1 unit here and 1 unit here. So there's 2 units of extra space that is too narrow to obviously fit anything in the obvious way. But it turns out if you start to jiggle them in some irregular pattern, some space will eventually open up and you can fit one more. It turns out, I'm not sure if 10.1 is exactly the value. Maybe it's 10.27 or something like that. But it's a phenomenon. And that packing will be very odd, irregular, random looking. It wouldn't be nice grid packing like the tiles on the ceiling here. It'll be all irregular. How many understand that? And generally, it's very, very difficult to solve this kind of problems. It's very counterintuitive. So even this kind of packing of spheres, maybe there's a way to jiggle them around and make it irregular and make it in some places where 1 won't touch 12. And over there, a mile later, it'll open up extra space, and you can put an extra sphere in, and that'll slightly increase the density overall of the entire configuration beyond what you would get if you do a regular lattice, like a crystal pattern. Now, so for 2 dimensions, the kissing number is 6. For 3 dimensions, the kissing number is 12. For 4 dimensions, we don't know what the kissing number is. For 5, we don't know. For 6, we don't know. For 7, we don't know. For 8, we don't know. For 9, we don't know. We know the number for 24. The number is 196,560 hyperspheres of 24 dimensions touch a central hypersphere of 24 dimensions, all equal size. That much we know only because there's something called a Leech lattice that has very regular structures, and that basically helps us solve this number in 24 dimensions. All the other dimensions we don't really know, which is kind of amazing. And even in 3D, the problem was unsolved for 3.5 centuries. Yeah. Okay, maybe they just resolved 8, and I haven't heard about it yet. But I'll look it up. That's an interesting observation. But all the other numbers are very, very difficult to come by. Of course, don't get me wrong. We know some stuff. We know upper and lower bounds on these numbers. But there's a big gap between these upper and lower bounds. And in general, it's very, very hard to tell. And when it gets to non-equal spheres, the problem is even harder than equal spheres. So far, we just talked about equal spheres. And if you talk about non-spheres, like M&M shaped, kind of oblong, ellipsoid kind of shapes, it's even harder than that. So it's a very rich area of very deep questions and even deeper kind of results. So this brings us to aperiodic tilings. So during Hilbert's time, we didn't even know that aperiodic tilings can exist. But an aperiodic tiling is basically a tiling that's not equal to any translation of itself. So if you have the plane tiled with aperiodic, in an aperiodic way, if you take that tiling and shift it over any amount left and any amount down, it will never be equal to itself. Of course, this is not true about tilings like the ceiling here. If you take this and shift it over one tile this way and one tile that way, it'll be exactly like the original, indistinguishable from the original tiling, assuming that, never mind the lights and the air conditioning ducts or everything, it's just the tiling itself. So an aperiodic tiling is not equal to a translation of itself, and there's something called an aperiodic tile set that only creates aperiodic tiling, and so the tile set itself is aperiodic, not just the tiling that it creates. So it's doubly aperiodic One is the tiling that he creates is aperiodic, but he cannot create any periodic tiling, so the tile set itself is aperiodic in nature. So the first guy that ever discovered an aperiodic tiling is Penrose, Roger Penrose, a famous physicist, mathematician in the early 70s. And here's the tiling that he discovered. Using these two tiles, basically two quadrilaterals made up of these angles, 72, 144, and so on. And these are the substitution rules based on these two tiles. And you can look at this in your spare time and kind of track all the details of that if you'd like. But here's an example of an aperiodic tiling from these two tiles. And if you look at this, no region of it is a translation of any other region of it, in the sense that you cannot take this tiling and translate any finite amount up and left and arrive at the same configuration as before. They'll all be unique. It's not that hard to prove it, actually, for this particular tiling. And that left open the question, is there a single tile in 2D that can achieve this effect, not a pair of tiles? Because tilings often have multiple tiles, not just one tile. The ceiling tiling is pretty boring. There's only one tile. It's this rectangle, and it's just repeated in regular patterns. This tiling has two tiles, and some tilings have more tiles than two. And just so you don't think it's just some abstraction, it comes up in architecture all the time. Here's an aperiodic tiling of a floor tile in some lobby. It appears on the tabletops of furniture, and even on the facade of buildings. And it makes a very nice architectural design element, because the eye keeps looking for patterns which aren't there. And so you kind of get mesmerized by this, and you kind of look for the periodicity or the pattern, and there is none. It's aperiodic, by definition. This too, right here on the table. Here's a pinwheel tiling made up of triangles, just a single triangle, and it creates this aperiodic tiling, which have interesting properties, like tiles occur in infinitely many orientations. Not all orientations, just an infinite number. There's also an infinite number of orientations where triangles do not occur also. There's no contradiction to these two statements, right? And the edge lengths are irrational and they're incommensurable, but all the vertices of all the tiles have rational coordinates, it turns out. And you can create, fractals from these kind of tilings as well, and it's a very deep mathematical field, tiling theory. And here's a building in Australia. It's in Melbourne, Australia, where the facade of the building is this aperiodic pinwheel tiling that we just saw on the previous slide. So architects are incorporating that into architecture all over the place, actually. And that brings us to higher dimensional tiling. So here's a 3D pinwheel tiling. So it's basically, you take a prism, prism shaped like a 3D kind of pyramid, and it turns out you can tile all of 3D space aperiodically using these substitution rules like that. And there's still an open question after that, whether there's a single tile aperiodic 3D tiling that doesn't admit any periodic tiling, because you can take these two figures right here, bring them together, and you get a parallelogram, and then use the parallelogram using these two together, because they would fit perfectly, right, like that. They use a parallelogram to then replicate like a ceiling tiles repeatedly, and now you'll get a periodic tiling, not an aperiodic tiling. The tiling would be periodic. And so that tiles the plane aperiodically, but it also tiles the plane periodically. And we still don't know to this day whether there's a single tile that tiles the plane only aperiodically and not also periodically and some other way to tile it. So here's the 3D again. And so for 2D it's open, I just mentioned that. For 3D it's been solved. So here's a single tile. It's called a biprism because it's two prisms connected back to back, two square base prisms connected back to back with an irrational twist. The twist is an irrational number of degrees, like pi degrees or something. And if you put them side by side, you get this kind of configuration. And then you stack them on top of each other, and they fit perfectly like that. And here's that irrational skew that I was telling you, the irrational twist. And you can keep stacking them up like this, layer by layer by layer, and they fill up all of space. And it can only fill up space in an aperiodic way. And because it's an irrational twist, any plane has a different twist than any other plane below it, because no sum of irrational numbers, no integer sum of an irrational number will give you a rational number all of a sudden, if you think about it. So that's actually more than what Hilbert asked for. So this field goes on. And then there's, of course, Wang kind of tilings. And it turns out that the tiling problem itself is undecidable. What's the tiling problem? I give you a set of tiles, and I ask you the question, does this set of tiles, is it possible with a set of tiles to tile the entire plane? No overlaps and no empty spaces. In general, it's undecidable. Now, the tiles could be constrained. So, for example, in this set of tiles, you can only put green next to green, like dominoes, right? Red next to red. So you can put these two pieces like that next to each other. You can put yellow next to yellow, but you cannot put blue next to yellow, and so on. The question is, could you tile the entire plane with this set of 13 tiles? And this set of 13 tiles will only tile the plane aperiodically. Now, you can always convert color constraints to shape constraints. What you can do is, instead of, if you have one tile like this and another tile like this, and you can say, well, this is red and this is red, and you must put them together like that. What you can do is say, because this is red, we'll call this a triangle, and this is also red, so we'll call that an indented triangle. And now you don't have to say red and red anymore. These two can only be put together next to each other, and other things can't, because other things will have other shapes, on them, or whatever, like jigsaw puzzles. You can make a jigsaw puzzle where the solution is unique. No piece will fit any other piece that it shouldn't. How many get that? So you can convert color constraints into shape constraints, and then you don't have to worry about colors anymore. So the two are equivalent. Saying there's color constraints is the same as saying you can make shape constraints that achieve the same goal, like a jigsaw puzzle. And so the tiling problem is undecidable, and that was kind of a surprise. But basically, the reason it's undecidable is that a tiling can simulate an arbitrary Turing computation. As you keep juxtaposing tiles together, you're essentially creating a Turing tape kind of situation where the color constraints are so the transition function. They determine what state can go next beyond a certain current state. And that's the next tile and the next tile after that. And the set of tiles altogether represent the Turing tape. How many sort of get the vague idea of what I'm talking about? I don't expect you to see all the details. It's hairy. But basically, a tiling, as you build a tiling, you're simulating an arbitrary Turing machine. You're basically constructing its tape from tiles, one transition at a time of the transition function by adding one tile at a time. That's the idea behind showing that tiling is undecidable in general. And there's lots of applications for aperiodic tiling. So, for example, in graphics, you have texture mapping. So you have one tile, and you can replicate it a bunch of times, but you can sort of see how it repeats. Your eye can sort of catch the pattern, kind of the repetition pattern, both sideways and vertically. But it gives you rise to textures that are not very interesting. They're kind of repetitious and kind of boring and contrived. But if you're using kind of aperiodic tiles to create textures, this set of tiles here is aperiodic, and it aperiodically tiles the plane, and you get textures now that look a lot more interesting and kind of random and kind of white noisy and not so regular and boring anymore. So they're used in graphics, in text generation, in animated movie design, and many, many applications to that. Here they're used to create real-time blue noise. And of course, you have versions of this tiling problem in arbitrary dimensions. So here's a set of 16 tiles, and they're really cubes. They're cubic, three-dimensional tiles, and these are all the flattened versions of it. Each one will assemble into a cube, and together they tessellate or tile all of 3D in an aperiodic manner, like that, for example. So you have arbitrary dimensions of these things, and like I said, you have applications in videos and graphics and geometric problems and self-assembly. A lot of applications of these kind of aperiodicity in tiling, and they also make very nice architecture and art and design. And so again, here's the kites and darts tiling of Penrose that we saw a few slides ago. And I'm going to show you a bunch of other tilings, just so you can see the diversity of tilings. They're not just about kites and darts. Or this one has three shapes: pentagon, boat, and star. Here's the pentagon, here's the star, and here's the boat shape. And together they tile the plane like that, aperiodically. And these are the substitution rules. You can sort of follow the recursive substitution rules and see how this tiling is constructed. Here's another one made of two pieces. They're both rhombuses, quadrilaterals, but slightly different. One is a little bit narrower than the other. And here's the color constraints converted to shape constraints, like I was doing out here on the board. Right? And here's a kind of recursive buildup of the tiling using these substitution rules. And you get this kind of a pattern, aperiodic pattern. Here's another one. This one is with kind of squarish, rectilinear kind of tiles. 3 different tiles, and the substitution rules are like that. So what is the substitution rule? Basically, you take this tile, and in this configuration, you put them together, these two like this, and it creates a slightly bigger version of this. And here, you could put these 3 tiles together, I guess 4 tiles, 3 of these, 1, 2, 3, and 1 of these here, and together they form a slightly bigger version of that. And similarly for this one, you take these 2 tiles here and 1 of these tiles here, and together juxtaposed like that, they create a bigger version of this. Then you recursively keep doing this. And it grows and grows and grows, and this is the end result in the limit of the entire plane getting eventually tiled like this. That's the construction rules, or the recursive composition rules. How many understand that, what's going on? Okay, so that's what this means here. Here's another tile. This guy, Robert Amann, back in the 70s, came up with a whole slew of different interesting tiling. Here's 2 pieces, rectilinear tiling. This one is 2 rhombuses. I think we've seen this one before. This one is 3 pieces, like that. This one, again, is 2 rhombuses. And you can see the diversity of tiling. Here's one made of triangles. Here's one made of 2 parallelograms. One is thinner than 3 parallelograms of different thicknesses, different proportions, I guess, or aspect ratios, if you will. And you get a lot of interesting tilings, aperiodic tilings. Again, the eye tries to find patterns, but you can't. There are no patterns there. It doesn't repeat. This one has 1, 2, 3, 4, 5, 6 different pieces. 6 different small tiles, and these are the substitution rules, recursive substitution rules. It's actually not easy to come up with these. Think about how you'd even find this out, from scratch. You'd have to probably spend weeks or months using computer searches and a lot of kind of artistic flair and trial and error and a lot of scratch paper, but it's fun. And when you discover them, you of course have to prove that this is true, that they do tile the plane. Once you discover something that works, it's not that hard to prove that it actually works. In nature, so when we discovered these kind of tilings, we thought this was, hypothetical kind of constructs, mathematical game, a toy, interesting, cool factoid. But it turns out that in nature, these structures occur naturally. They're called quasicrystals. How many heard of quasicrystals? So it turns out that most crystal structures have a 6-fold symmetry, like snowflakes, for example, 6-fold symmetry. Diamond is, hexagons made of carbon atoms, right? Most crystal structures in nature have a regular repeating pattern. They're not aperiodic. But it turns out there's also aperiodic crystals in nature that look like this with a 5-fold symmetry, and they don't repeat. How many knew that? Nature produces aperiodic crystals. Now you know. But don't feel bad if you didn't know. All of humanity didn't know up until about 25 years ago. In the 90s, we finally discovered quasicrystals in nature. Not on paper like Penrose did in 1973, 74. This actually happens. But before Penrose and others came up with aperiodic tilings, we didn't know to look for them in nature, so we didn't discover them. Or when we saw them, we didn't know what we were looking at. We just thought it was amorphous stuff like sand or whatever. We didn't recognize that they were actually aperiodic tilings that have these properties. So this is an interesting kind of connection with the natural world that we didn't know about. based on these theories. And they can get pretty esoteric. Here's another one. This one is more rectilinear. Again, this looks almost repetitive, but it's if you count the number of, say, blocks here, 3, 2, 3, 2, 2, 3, 2, 3, 2, 2, 3. If this number, if you write that number like a decimal number, like 0.32322322, what kind of a number will that be? Irrational number. And all of them will be irrational. If you do it top to bottom, it'll be irrational again. There's no repetition. So it's just amazing that these things even exist and that they can be, moreover, created from just a few small pieces. We didn't realize that can happen. Actually, we thought that all tilings are like the ceiling, kind of boring. And you could have different tiles, like honeycomb is just hexagons repeated, but that's kind of boring too. We didn't know about these guys, and these have many other applications. So. Just to show you the diversity, some of them are not even rectilinear. They have odd shaped, completely odd shapes. This is like nautilus kind of shape, like snails or whatever, sea slugs. But this is aperiodic, and the recursive rules are right there. How to construct them. So another application of, just to give you the diversity of real life applications of this. So. When you have, why is glass so brittle, right? Glass kind of, you hit it with a hammer, it cracks, and the whole thing shatters, like a window of your house or whatever. But other materials are much stronger, right? There's kind of bulletproof kind of glass that even if you hit it with a sledgehammer, it will not shatter into pieces, because fault lines in glass travel very quickly and very far. If it's a regular lattice structure, it travels right down the fault line where all the crystals, form this nice, fault lines in between them. But if you have an aperiodic kind of crystal, any fault line that starts going somewhere eventually gets stopped. It doesn't travel very far. So this fault line here, it gets stopped over here. And this fault line stops here, and this fault line stops there. So the material becomes much, much stronger if you make it from an aperiodic kind of crystalline structure. So you can have glasses and materials that are bulletproof, much more thin, much more strong than normal materials, if you can construct them in an aperiodic kind of crystalline way at the at the atomic or molecular level. So there's lots and lots of applications. You get very strong materials, whether they're glasses or metals or plastics or whatever, what have you. So again, here's some more. And you can sort of see how fault lines don't travel very long before they come to an abrupt end. And so fractures and cracks won't propagate very far here, and it'll be a much stronger material. Anyway, so all this comes out of, Hilbert's, 18th problem or whatever about tilings and space filling and packing. And this is an ongoing, thriving area of research. There's probably conferences about this every year. This is kind of a sphinx-looking kind of tile with a single piece. Again, aperiodic. I'll just breeze through the rest of them. I got very excited about it. That's why I have so many, examples of it. It's kind of cool to write a program that, given a set of tiles, will find some aperiodic tiling of the plane. Anyway, I'll let you look at the rest of this at leisure. All right, that was problem number 18. So problem number 19, solutions of Lagrangians. So the rest, these problems would just kind of list here, but not dive too deeply into. There's things about calculus of variations, and some are resolved, some are partially resolved, some are still, being worked on. But so a few years ago, DARPA, not to be outdone, by Hilbert, issued their list of 23 problems in the year 2000. Right? And jokingly, these problems are called, DARPA-hard problems, like NP-hard problems. DARPA, of course, is the Defense Advanced Research Project Agency. They create a lot of the, technologies that eventually we all know and love. And they have kind of a military flair originally, but later they come into wide civilian use. Can anybody name a ubiquitous technology created by ARPA? The internet. How many knew that? DARPA created the internet back in the 70s. And the reason they created the internet, and the reason they even created packet switching that runs the internet, TCP/IP packet switching, some data gets broken into hundreds of different packets, and they all get sent, and it can go arbitrary routes and take different paths across the network, and at the end, at their target, they get reassembled into the original message. What was the idea behind it? Why would you do that? Break a message into hundreds of pieces and send them all individually.
To make sure that communications between two, I guess, military officers are always guaranteed.
Yeah, it's very robust. So if a piece gets lost, it gets retransmitted, and you don't have to retransmit the entire original message. And it doesn't matter what path the pieces take, eventually they get reassembled back. Each one is numbered like a jigsaw puzzle, and at the end, at your destination, the puzzle is reassembled into the original message. It's a very, very robust protocol with lots of resiliency and fault tolerance. And the reason they made it that way is they wanted to be able to still communicate after a nuclear exchange, after a nuclear war, right? Usually it'd be the Soviet Union versus the United States back in the 60s, the 70s, the 80s. So basically it was a communication protocol that could withstand nuclear attack. So if one city was taken off the map with nuclear warheads, all the packets would reroute around it through other cities and still be assembled at the target. So it's an interesting, very, very resilient protocol that can withstand nuclear attack, actually. So when some country tries to censor the internet by taking down nodes and hubs and routers and block certain paths and links, the TCP/IP protocol gets around the censorship. So it basically treats the censorship as damage and routes around it. So not only it's an anti-nuclear attack protocol, it's an anti-censorship protocol for exactly the same reasons. And some countries haven't figured that out yet. And they're still grappling with all that, trying to censor the populations, and good luck to them with that. I mean, they can do only partial job of that, and mostly through intimidation, not technologically. It's not possible. Okay, so here are the 23 problems that DARPA, have come up with, and the reason it's even 23 is because it's homage to Hilbert, because his list had 23 things on them. And look at that, number 19 on DARPA's list, the Riemann hypothesis. Again, they just threw it in there for good measure. So that problem, it appears on every list, right? It appeared on Hilbert's original list, it appears on DARPA's list, and of course it appears on the Millennium Clay Institute, the Millennium Prize list. It's worth $1 million on that list. So that's kind of a perennial open-ended problem. And just so you see DARPA's list at least once, I'm going to list that very quickly here. High-dimensional mathematics, 21st century fluids, so non-Newtonian fluids like foam, suspensions, gels, liquid crystals, right? Biological quantum field theory. Occam's razor, look at that, appears on their problem number 7. Protein folding, that's a tough problem. Even if you know the structure of the protein, you still don't know quite how it folds together. Self-assembly, quantum computing is on there halfway through. Game theory that scales, that'll be nice to have. Geometry of genomes. Right. There's this Riemann hypothesis number 19. So that's DARPA's open problems, and they put a lot of money. They put billions of dollars on. It's not quite a bounty, but research grants for people, research groups, universities, researchers to work on all of these problems, and people are working on all of these problems, and that brings us to Gödel. Yeah.
What was the problem concerning quantum computing?
Just mostly to get it to work. Algorithms, figuring out more quantum. Right now we just have a few quantum algorithms. We have one for factoring and one for doing search, Grover's algorithm, but generally we don't have a large library of quantum algorithms. In fact, the whole notion of quantum computer architecture is very nebulous right now. People have some prototype machines with a few qubits. There's even some companies like, was it Q-Wave or P-Wave? Some companies sell you a quantum computer, quote unquote, for $20 million, and there's some debate about whether it's a real quantum computer or just some toy kind of contraption that can do very limited things. It's usually the latter. Still, I mean, it's not a fraud, but it's not a full-fledged quantum computer, and it's not even clear yet what the best quantum, computer architectures would be, and what kind of algorithms you'd run on them, and it's all being explored, and it's a pretty new field. It only came out in the mid '90s or so, with Peter Shor, coming up with a factoring algorithm for quantum computers, but that still didn't define what a quantum computer would look like, what an operating system would look like, what the architecture would look like, and there's different versions of, it's the entire conferences on this thing, and ARPA is spending a lot of money on this. So is Google. So is every major government, basically, simply because it's a very high risk but high return proposition. So yeah, it's expensive and it's unclear and it's in its early stages. But if anybody cracks that problem and produces a real quantum computer that works reasonably well, they'll probably make trillions of dollars, or worse, they might be able to crack every crypto algorithm known to most crypto algorithms known so far. So that depend on computationally difficult problems like factoring and formality testing and so on to operate. So that's one of ARPA's. So these problems are kind of fuzzy. It's not like this one is not fuzzy. The Riemann hypothesis is a very precise definition. Are all the roots, the non-trivial roots of the zeta function have real part equal to a half? There's nothing ambiguous about that. The answer is either yes or no, and you got to prove it one way or the other. But the rest of them are kind of open-ended, kind of fuzzy. I'm sure in a century or two from now, people will still be working on quantum computing, and they'll probably have various working prototypes and even many products, and maybe the computers in our pockets in 2 centuries from now, our great grandkids will carry quantum iPhones, Q phones or something in their pockets. Who knows? But these are kind of open-ended. Most of these, they're mostly research directions, not exactly individual, well-defined, crisp problems. But many crisp problems and specific research topics fall out of these areas, and so it's kind of an interesting, robust set of directions, basically. All right. So let's take a short break for 10 minutes or 15. Is that that's not the right time, is it? What time is it right now? 6:14. Okay, so I guess it's off by an hour still. All right, let's come back at 6:25, I guess, and continue with this discussion. By the way, the third homework is due Saturday, this coming Saturday, and then the midterm will be released around that time on the weekend. And then you'll have a week time window to work on it for 6 contiguous hours. So the work time is only 6 hours, but you'll be familiar with most of these problems. Most of these problems will either come directly from the problem sets posted on the website or be very minor variations of them, just like the homework problems. And so there should be no surprises if you're solving lots of problems. You don't need to worry about it. It'll be more of the same. So let's come back in about 10 minutes and continue there.